Three words nearly killed one of the greatest sports cars ever built. By February 1989, Honda's engineers believed their NSX prototype was essentially finished, an all-aluminum mid-engine machine engineered to challenge Ferrari and Porsche. Then, the reigning Formula One world champion drove it around Suzuka and told them the chassis felt a little fragile. That single assessment from Ayrton Senna forced Honda to tear open a near-production chassis and increase its rigidity by 50%. The question isn't whether he was right, it's what those words revealed about a flaw Honda's own engineers never felt. In the late 1980s, Honda set out to build a vehicle that would fundamentally redefine the high-performance sports car market. Under the direction of project leader Shigeru Uehara, the engineering team aimed directly at established European benchmarks, targeting the precise handling and speed of Ferrari and Porsche. Their design was a radical departure from traditional steel frames. They engineered an all-aluminum monocoque chassis, the first of its kind for a mass-production vehicle, housing a mid-mounted V6 engine with double wishbone suspension. This incredibly lightweight structure promised the agility of a dedicated racing machine, but with a level of daily usability and mechanical reliability that European exotics had historically ignored. By early February 1989, Uehara's team had spent nearly a month conducting intensive track testing at Honda's own Suzuka circuit, refining the chassis dynamics, weight distribution, and suspension geometry. The telemetry data and laboratory stress tests all pointed to the same conclusion. The project had met every internal technical target. The vehicle was fast, remarkably stable through high-speed sweepers, and highly compliant on real-world roads. In the minds of the engineers, the balance between ride comfort and structural stiffness was fully optimized. They had verified the design using advanced computer simulations and thousands of physical test miles. The prototype was on schedule, the engineering parameters were locked in, and the car was deemed ready for production. Honda's development culture, highly disciplined and buoyed by their dominant Formula One engine partnerships, had produced a machine they believed was flawless. They were entirely confident they had built the most advanced sports car in the world. In February 1989, the environment at the Suzuka circuit was dominated by the high-pitched wail of Formula One engines. McLaren Honda was conducting pre-season testing for their new MP45 chassis, powered by Honda's naturally aspirated V10 engine. Behind the wheel was Ayrton Senna, the reigning Formula One world champion. Senna's partnership with Honda was defined by extraordinary performance. His 1988 championship campaign had yielded 15 victories in 16 races, establishing him as the ultimate authority on vehicle dynamics. Knowing Senna was running laps on the same track, the Honda research and development team recognized a rare development opportunity. Shigeru Uehara's engineers brought their near-production, unbadged NSX prototype directly to the pit lane. The vehicle had already cleared every internal engineering milestone, but the development team sought to validate their achievements against the standards of the fastest driver in the world. Senna joined the session strictly as a technical benchmark, rather than a marketing figurehead. To Honda's engineers, his acute sensitivity to chassis behavior, steering weight, and suspension feedback made him a precise, living diagnostic tool. He possessed an uncanny ability to read how a chassis transferred its weight, how tires reacted to slip angles, and how a metal structure resisted twisting under extreme cornering forces. As Senna climbed out of his Formula One cockpit and stepped into the all-aluminum prototype, the atmosphere in the pit garage was filled with quiet confidence. The engineers stood ready with their clipboards, fully expecting their calculated perfection to be validated by the world champion. Senna buckled into the prototype and set out onto the Suzuka circuit, pushing the all-aluminum machine through its paces. The development team watched from the pit wall as the unmarked silver car rounded the high-speed curves of their home track, expecting the champion to confirm what their instruments had already told them. When Senna returned to the garage, he was initially cautious, hesitant to overstep his role as an F1 racing driver, commenting on a mass-production road car. But his technical assessment was uncompromising. He told the gathered engineers, "I'm not sure I can really give you appropriate advice on a mass-production car, but I feel it's a little fragile." The feedback struck the engineering team with immediate, devastating force. To a group that had spent years calculating, simulating, and validating a chassis they believed was completely finished, the word fragile was a profound shock. In a single, quiet sentence, Senna's extraordinary physical sensitivity to vehicle dynamics had exposed a structural shortfall that Honda's advanced computers had completely missed, leaving the once confident development team entirely speechless. Under the skin of the prototype, the issue Senna felt was a fundamental characteristic of vehicle physics. When a car enters a bend, the front tires steer into the turn, while the heavy mass of the engine and passenger cabin resists that change in direction. This creates massive opposing lateral forces between the front and rear axles. The resulting physical deformation is known as torsional flex, the actual twisting of the vehicle's frame along its length. When a chassis experiences torsional flex, it acts like a giant metal spring. When a driver turns the steering wheel, the energy of that input does not immediately change the car's direction. Instead, the force must first twist and wind up the frame before the energy can travel through the suspension to the tires. This flex introduces a microscopic delay in the car's dynamics. The driver turns the wheel, the chassis twists, and only after that momentary hesitation do the tires load up and change the car's trajectory. This structural twist also alters the suspension geometry mid-corner, changing the precise angles of the tires when they require maximum stability. For a typical driver on public roads, this subtle delay is completely undetectable. Standard road tires have soft sidewalls that naturally flex, and everyday driving speeds never generate the extreme cornering forces needed to bend a solid metal frame. In fact, most road cars are designed with a degree of structural play to help absorb bumps and maintain ride comfort. To the average driver, Uehara's prototype would have felt remarkably precise. But Ayrton Senna's sensory baseline was calibrated to a carbon fiber Formula One chassis. In his Grand Prix car, the structural stiffness was so immense that steering inputs resulted in instantaneous changes of direction. The connection between the steering wheel and the tire contact patch was direct and unyielding. When Senna pushed the aluminum prototype through Suzuka's high-speed ESCs, his hands and inner ear immediately registered that brief moment of chassis deflection. What the development team had designed as a comfortable balance for a road-going sports car, Senna felt as a physical delay. To a driver operating at the absolute limit of traction, that momentary disconnect between input and reaction made the vehicle feel unstable under load. For Shigeru Uehara and his development team, Senna's assessment was a direct pressure on their professional reputation. These disciplined engineers had spent years pioneering the world's first mass-production all-aluminum monocoque, sacrificing years of labor to meet Honda's strict targets. They had verified every parameter through advanced laboratory stress tests and thousands of physical track miles. To have their near-production masterpiece described as fragile by an outside driver, even one of Senna's status, shook the team's confidence. In most automotive companies, such late-stage feedback would have been defensive fodder. It would have been easy to argue that Senna's senses were skewed by his daily drive in a carbon fiber Formula One racer, or that a road car required a level of compliance that made some flex necessary. But Honda's R&D department operated under the strict discipline of Kaizen, the philosophy of continuous improvement. There was no room for corporate denial or defensive arguments. Instead of defending their blueprints, Uehara's team chose to treat the feedback not as an insult, but as an objective design mandate. They did not debate whether the champion was right. They accepted that their calculations had missed a variable that only human hands could detect. The word fragile reframed the entire project from nearly finished to not good enough. Rather than rushing to a compromised launch, the engineers prepared to pull the prototype apart and rebuild the chassis from the ground up. Uehara's team returned to the drawing board, treating Senna's critique not as an obstacle, but as a set of precise coordinates for structural refinement. Over the next 8 months, the research and development department focused entirely on the aluminum space frame. They did not settle for minor adjustments or simple suspension tweaks. They launched an extensive re-engineering of the entire load-bearing architecture. To transform a highly advanced but physically flexible chassis into a truly rigid platform, the engineers targeted the areas where lateral loads placed the greatest stress on the metal. They concentrated on the car's midsection, beefing up key structural nodes. Engineers selected extruded aluminum sections with thicker walls for the B-pillars and the door sills, creating a much stronger passenger safety cell. They reinforced the front and rear bulkheads, ensuring that the connection points for the double wishbone suspension could resist deflection under extreme G-forces. Behind the cabin, they added a dedicated rear floor brace that bridged the engine bay and linked the rear bulkhead to the main frame, completing a closed loop of structural resistance. Executing these major modifications required a complete overhaul of the manufacturing tooling and welding techniques. This was a massive technical and financial gamble for a vehicle already so close to its scheduled production sign-off. The results of this intensive 8-month overhaul were measurable and profound. When the team subjected the redesigned monocoque to laboratory stress tests, they discovered that the overall torsional rigidity had increased by approximately 50%. This was not a minor marginal gain. It was a massive structural leap that completely altered the vehicle's dynamic behavior. By elevating the torsional modulus to this level, Honda's engineers had created a platform that was at least 50% stiffer than its main European benchmark, the Porsche 911 of the era. The new structure could handle extreme lateral forces without compromising the lightweight advantages of its all-aluminum design. With a frame that resisted twisting under load, steering inputs would now translate instantly to the road. The suspension could maintain its carefully calculated geometry without the chassis itself acting like an unpredictable spring. By refusing to dismiss Senna's feedback, Honda had successfully translated a driver's subjective sensation of fragility into concrete, quantifiable engineering data. They had turned a potential structural weakness into a defining technological achievement, proving that their commitment to absolute precision was stronger than their engineering pride. Honda invited Ayrton Senna back to the pit lane, transitioning his role from an external critic to an active development partner. The team split their testing schedule between the high-speed curves of Suzuka and the unforgiving, uneven tarmac of the Nürburgring Nordschleife in Germany. With the chassis flex resolved, the focus shifted entirely to suspension geometry, damping curves, and transient handling balance. On a rigid platform, the existing springs and dampers reacted differently, requiring an entirely new calibration. Senna ran consecutive laps, returning to the garage to dictate precise adjustments to the shock absorbers and anti-roll bars. The engineers fine-tuned the front roll stiffness by 26% and the rear by 19% to match the new chassis dynamics. This collaborative loop of track testing and immediate adjustments allowed Senna to help dial in the car's final breakaway characteristics at the limit. Rather than merely pointing out flaws, he worked to shape how the vehicle communicated with the driver. By the time the final suspension settings were locked in, Senna had effectively co-authored the dynamic signature of the production NSX. The production NSX arrived in showrooms as a vehicle that completely redefined high-performance parameters. The 50% increase in chassis stiffness, prompted by Ayrton Senna's initial feedback, yielded a machine defined by absolute cornering precision and high-speed stability. Most mid-engine sports cars of the era were notorious for sudden, unpredictable breakaway behavior at the limit of traction. The engineered rigidity of the NSX space frame gave the driver clear feedback and complete control, making extreme performance approachable for everyday drivers. This predictable handling, paired with daily reliability, directly threatened established European standards. While the Ferrari 348 and Porsche 911 demanded constant maintenance, heavy controls, and physical tolerance, the NSX offered comfortable cabin ergonomics, excellent visibility, and dependable Honda mechanics. It proved that exotic performance did not require fragile build quality, forcing European manufacturers to rethink their engineering philosophies. Senna's connection to the vehicle remained personal long after development ended. He kept 3 production models at his homes in Portugal and Brazil, including 2 in black and 1 in red, using them regularly as his personal transport. The global status of the NSX, as a landmark machine that made exotic performance highly usable, traces directly back to the structural revisions of 1989. By translating a driver's subjective feeling of fragility into objective structural reinforcement, Honda's engineers bypassed traditional vehicle development limits. The final vehicle challenged the world's best and permanently altered the expectations of what a supercar could be. Today, as modern performance cars use software to mask mechanical flaws, the original NSX remains a masterclass in chassis dynamics. It proves that technological advancement is nothing without the humility to listen to the driver. When engineering pride yields to pure human feedback, machines transcend their specifications. Did Honda build the ultimate analog supercar? Let us know your thoughts in the comments below.